Likewise, to how Nicholas Copernicus introduced the heliocentric model, another astonishing amendment in how we may decipher the universe could emerge, beginning a conversation known as the development of cosmology. This rise is marked by basic aberrations in our assessments and perception of the universe's essential properties, like its age, size, and speed of development. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has ignited this conversation with a picture that challenges material science. So, what exactly is this crisis, and how does the James Webb Space Telescope add to it? Well, adding to it is somewhat of a deception. It's more like a review that has been in progress. The crisis refers to how our understanding of the universe is tested, particularly regarding its age and size, which are associated with an extensive security buffer. The introduction of the JWST has been crucial in this context. Previously, we were limited in how far we could see into the early universe. However, with the JWST's advanced capabilities, space specialists can explore more distant galaxies, providing us with new perspectives and challenging some of our past assumptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming. This provides crucial data that can either support or challenge our current models of the universe. To understand the crisis in detail, it is critical to explore the context. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda-cold dark matter lambda-CDM model, has been particularly successful in explaining various aspects of the universe, from gravitational lensing to the structure of the cosmic web and the development of galaxies. The lambda-CDM model proposes that the universe began with a Big Bang followed by a period of rapid expansion and has been expanding ever since. It includes elements like dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, every notable observation, especially with cutting-edge instruments like the JWST, raises the possibility that our current model may be inadequate or in need of an update. The lambda-CDM model makes specific predictions about the properties and behavior of galaxies at different stages of the universe's history. For example, it predicts that galaxies in the distant past should be smaller, less developed, and contain fewer heavy elements compared to those in the nearby universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time to occur. Scientists have found inconsistent evidence challenging these assumptions, resulting in a crisis in cosmology. This crisis revolves around uncertainty about the universe's age, as different assessment techniques yield varying results, leading cosmologists to grapple with these discrepancies. To address this issue, researchers employ several methods to measure the universe's age. One method involves studying cosmic background radiation, unraveling the universe's developmental history, and using mathematical models like the Friedmann equations, based on Einstein's theory of general relativity, to determine the expansion rate and thus the universe's age at different times. The cosmic microwave background, CMB, a remnant radiation from the universe's early days, is a vital tool for this calculation. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer crucial insights into the universe's composition. However, these maps lack data on dark energy, a significant component of the current universe. Despite this limitation, researchers can use the Friedmann equations alongside various observations to estimate the expansion rate at different times and ultimately determine the universe's age. Another method involves observing exploding stars, specifically type Ia supernovae, which serve as standard candles due to their known intrinsic brightness. By comparing their known luminosity to their observed luminosity, astronomers can determine their distance, and thus the universe's expansion rate at various times. This technique, pivotal in the 1990s, led to the discovery of dark energy, now essential for cosmological calculations. While useful in determining the Hubble constant, a measure of the universe's expansion rate, discrepancies remain. Although not exactly constant, the Hubble constant is critical in charting the universe's expansion since the Big Bang around 13.8 billion years ago. NASA notes that the implications of this rate are significant. If the expansion is slowing, it suggests the presence of an unknown force, possibly dark matter. Conversely, if the expansion rate is accelerating, it could indicate dark energy's influence. In January 2018, researchers found intriguing results. The Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower rate in the more distant universe. This discrepancy underscores the universe's vastness and reminds us of Edwin Hubble's pioneering work, who first proposed the universe's expansion rate in 1929. Hubble's observations revealed distant galaxies moving away from us, illustrating the expanding universe, a cornerstone of modern cosmology. Initially, expansion measurements relied on limited data. However, technological advances such as the Hubble and Gaia telescopes have enabled more comprehensive observations, refining these measurements. Various telescopes use CMB readings to calculate the constant, although this method has limitations due to supernova availability for distant observations, limiting our universe's view. Since the discovery of dark energy in the 20th century, researchers have grappled with inconsistencies between these two approaches to the universe's age and expansion rate. As measurement technology becomes more precise, smaller variations arise, driven by more advanced systems. However, this progress raises more questions than definitive answers. Despite minor differences, only 10 to 20 million years separating estimates, the universe's 13.77 billion-year age warrants careful evaluation. One possible explanation for this discrepancy is potential flaws in CMB measurements. Despite being one of the most reliable measurements, it has been extensively tested since its launch in 2009 to validate its accuracy. Another perspective suggests a gap in our understanding of dark matter, raising the possibility of fluctuations over time linked to dark energy or another unknown factor. This potential has prompted various experimental investigations. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Resolving this uncertainty in supernova models could help address the measurement disparity. The crisis in cosmology has been further exacerbated by the discovery of the James Webb Space Telescope. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding, implying that our scientific comprehension requires a complete overhaul. However, the issue is that we have no idea where to start. To grasp the extent of this scientific revolution, we must look at the universe's origins. Around 50 million years after the Big Bang, stars, black holes, and star clusters began to emerge, possibly even as early as 50 to 100 million years later. Yet, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning 400 million years after the Big Bang. Ongoing JWST images reveal galaxies much older than the standard cosmological model predicts, suggesting a major update is needed. It is clear that the development of cosmology is at a pivotal crossroads. As observations challenge long-standing theories, scientists are compelled to rethink the universe's timeline, its structure, and the underlying forces that govern it. While tools like the James Webb Space Telescope, JWST, offer unprecedented glimpses into the distant past, they also raise profound questions that have yet to be answered. Telescopes like the JWST are uncovering phenomena that our current models of the universe struggle to explain. The ability to observe galaxies from just a few 100 million years after the Big Bang suggests that galaxy formation may have occurred much faster than predicted. These findings imply that the processes driving galaxy evolution are either more efficient or involve factors not accounted for in the lambda-cold dark matter (lambda-CDM) model. The lambda-CDM model, while successful in explaining large-scale structures and cosmic background radiation, is now under scrutiny. Observations of early galaxies that appear larger, more developed, and richer in heavy elements than expected suggest that either the initial conditions of the universe were different, or the timeline of star and galaxy formation must be reconsidered. If the model requires adjustment, it could mean revising our understanding of dark matter, dark energy, or even fundamental physics. One of the most debated issues in modern cosmology is the discrepancy in measurements of the Hubble constant, h. Local measurements using type Ia supernovae and Cepheid variables yield a higher value than those derived from the cosmic microwave background, CMB, radiation observed by instruments like the Planck satellite. This Hubble tension suggests that our understanding of cosmic expansion might be incomplete, or that unknown factors are influencing the universe's growth. Dark energy, responsible for the accelerated expansion of the universe, remains one of the greatest enigmas. If it behaves differently over time or interacts with dark matter in unexpected ways, it could reshape our theories about the universe's fate. Similarly, dark matter's elusive nature continues to perplex scientists. Hypotheses range from undiscovered particles to modifications in gravity, but a definitive answer remains out of reach. To resolve these cosmological crises, several avenues are being explored. Gravitational wave astronomy opens new possibilities for studying the universe's structure and the behavior of massive objects like black holes. Next-generation observatories such as the Vera C. Rubin Observatory and the Euclid mission will provide more precise measurements of dark matter and dark energy distributions. Theoretical innovations beyond the standard model, including modifications to general relativity or alternative explanations for dark energy and matter, may be required. As we continue to push the boundaries of observational and theoretical cosmology, humanity stands on the brink of potentially revolutionary insights. Whether through refining existing models or developing entirely new frameworks, the coming years will likely redefine our understanding of the universe. The current crisis is not